All right, hello everybody. I'm here with my good friend Raminda Madura. I've worked with Raminda for over, I guess, 15 years at least, starting with his the first venture. What was the name of that?
It's Tier
Logic, that's right.
Almost
Yes.
20 years ago.
20 years ago. So Raminda raised about 15 million for
We
that.
raised 15 plus 7, about 20 million in total.
20 million.
Yeah.
So Raminda is a seasoned entrepreneur who knows how to get companies moving, and he's now currently doing a new application, a new company that deals with acceleration of AI processing on a processor, or the trade name for that is AI CPU, as we call it. So welcome, Raminda.
Good to be here. Thank you.
Yeah. I'm not so sure that I fill in all the relevant details, but maybe if you want to kind of add anything else that might be of interest.
So my background is obviously in computing. I have 30 years of working in chip companies, and I've done 360 of chip work. As a result, we have worked on designing, technology development, manufacturing, customers, the whole work of things. And lately, we are working more on architectures and computing techniques. And that has led to this new work that we are doing, which
Fantastic.
is how do we come up with a different way of doing AI computing.
Well, tell us a little bit more about the specific challenges of why Nvidia couldn't do what you're doing.
So what we are doing goes back into a simple question we decided to ask. Why other people didn't ask that question, I don't know. But we asked the question. For a good 30 years of our life, everyone has been very happy with CPUs. People learned how to write software programs, and CPUs had this technology of compilers. So you could break it down and somehow or other run it from the code in hardware. And this has worked very efficiently for a number of years. Suddenly, it stopped. And the argument has been, why did it stop? And the answer was very simple. People came up with applications that required far more compute capabilities than what a CPU could do, and the CPU could never keep up with it. It's architecturally, it was too weak to keep up with the massive parallel computing that was required by AI. In parallel, there was a different technology, the GPUs. They were not doing general purpose computing. They were doing a lot of parallel computing for graphics processors.
Right.
So all of a sudden it came a de facto choice, because suddenly you could use this other thing you were doing for graphics processing to come in and help with the workloads of a GPU.
Right.
As a result, we end up with today's world where you have a CPU plus you have a GPU to doing all the AI workloads, and other take-offs, spin-offs of that has come up with the neural processor network unit, or a TPU, tensor processor unit, and in-memory computing, all these other techniques. But at the end of the day, it's because CPU cannot do certain workloads, so you bring another system. And eventually, you have to now manage a two-system solution.
Right.
So we asked a simple question. If a CPU had been able to do this, such as an AI CPU, for example, if there was a magic CPU that was an AI CPU, then why would you even bother?
That's right.
Looking at a second compute system? And everyone would have been perfectly happy, would have marched along for another 20, 30 years. And then you have to further analyze it and say, things got very complicated when you ended up with two compute systems, because you have to write your code to fit into two computing spaces. You have to do extra software to map from one to the other, copy from one to the other. Power went up, the energy went up, everything got way too complicated.
Right.
So if you were to merge it, would that actually disappear? And suddenly would it become a much simpler system to handle? And of course, now that we are well into what we are doing, that we find out that is indeed the answer. Our software becomes so much simpler. We don't need
That's right.
8,000 CUDA software engineers developing an entire environment to do our work. We
Right.
can do it with just 4-5 lines of code. Be done, and efficiency improves, the power footprint comes way down, the complexity comes down, so everything is much better, right? So that we're very happy with that, how it panned out because of that simple question we asked.
Well, that's a fantastic and very powerful idea. I mean, we know that software such as OpenClaw exploded in the market really in December of 2025, and it just took off. And now, everybody in the in the world, but a lot of them is U.S. and Chinese. They use OpenClaw, and apparently Apple was lucky enough to fall into this spot where OpenClaw could be used at a home setting where it's very low power. If you use an Nvidia GPU, it's going to be like massive. I remember I did this when I was training the GPT-2 technology back in the COVID era, and my electricity bill from that computer was like $800 a month back in 2020, I think, something like that. Massive amount of electricity.
Now the compute power is even higher.
Yeah,
because
yeah.
they're doing more computing.
Yeah. So now with your chip, it would be fantastic because I'm paying an arm and a leg for these mini PCs with 128 gig of RAM to do the inference, and and I had to buy yet another one so that I can augment those two together and run tasks locally. And I think that's the future. The future is that you have, instead of using cloud, and you're always going to use the cloud for the most powerful function, but a lot of those simpler functions you definitely could run at home and you save yourself money. So yeah,
yes,
that's a very so your vision would fit very well with that.
Yes, and that's a very powerful story, because if you look at a lot of individuals, including myself, right, we are very reluctant and very hesitant to put our private information out there in the cloud. As it is,
right,
against our well-wishers, our information does get posted in the cloud, which we don't like, right? There's no help. So why would you willingly want to do that? Then comes the second question. For a lot of things that I do, I really don't need to know what the Queen of England is doing today or what somebody in Australia is doing the other day, right? I just need to know, what am I doing? What did I do yesterday? Where is my writing taking me? How can I find what I write quickly, effectively? So basically what I'm saying is I need a custom. My private custom assistant. Who can tell me, go to see the doctor today, go take these pills tomorrow, here's your education plan, go take this class, your homework is due tomorrow. Everybody needs this, right? And the next level of that is, how do I connect it to people I do know, my relatives, my family, my friends. So these are private data centers, if you will. It's your home data center.
Well, it's no different than, let's say, in the 60s, you used to do things on a mainframe. You had to rent your time. And then in the late 70s, early 80s, the PC came out. And then, it started, changing the concept of where you can do your compute. And I think right now we see that same trend, which is, well, the most powerful model, you have to go on a cloud. You have to go on a big computer. But eventually I see that your technology could be utilized in not just in a home setting, but possibly long-term, maybe 10, 20 years from now, in a wristwatch device where you have local processing.
Absolutely, because it all boils down to how large is your device and what is the power consumption and the footprint of the device, right? So if you take the size, weight, and power factor and cost, the swap-C of a solution, the smaller it gets, the better it fits.
The more powerful it gets.
And more powerful it gets, and the better it fits into all walks of applications. So in that environment, all these things can be connected to each other, providing help and feedback into it, And just the other day, I think there's an announcement from Nvidia where Jensen comes and says, I see the day when there are agents and your
Yes.
private assistants running your own things and telling you
Yeah.
what to do on a day-to-day basis. So then you have to ask the question, if that were to happen, do you want 1,000-watt?
You're not gonna wear a watch with a car battery behind
That's
you.
not going to happen, right?
Right.
So then you have to say, oh, I need my solution to be at, let's say, under 10 watts of power
Right.
for it to run in some small battery format. And then the next question is, for that to happen, what are you willing to sacrifice? So if you go buy an AI PC today, for it to run at the 30, 50 or 60 watts of power, there are many sacrifices you have to make. One of them is your precision comes way down to 4-bit quantization.
That's right.
So that is a precision where certain applications will not allow you to be that poor. For example, a medical device, if it lost that much of accuracy, will not give you the correct type of advice.
That's right.
If you happen to be a drone that needs pinpoint accuracy in any other application or a missile, it will not allow you to have this kind of error,
Right.
so that you end up with friendly fire versus enemy fire. Right? So
Right.
there are multiple applications. And finally, there are so many regulations that says you are not allowed to share your information, even if it's in the cloud, to get any work done from the cloud. So what are you going to do with all those kinds of privacy regulations? There are lots of it. Europe has
Yes.
more of it than in the US. But even in the US, you probably have attorney-client privilege information that you don't know
Right.
whether you can post it in the cloud to get it, right? So that's one area. And the second one is, there's so much research going on nowadays. AI is changing so quickly, so fast. And the usual application is you take a foundation model, maybe it has 500 billion parameters, it's huge, needs tens of thousands of watts, fine. It's in the cloud. You take it,
Right.
but you build a smaller version of it, a 30 billion parameter model. And that you train it into a very specific area of your application. So
Right.
I'll take drone as an example. So you train it to be a drone. And that drone, then you have to ask, so what's the right model parameter I need? And it depends on what decision do you want to do.
Right.
If you want an intelligence at the point of application, then you need at least a 30 billion parameter model or bigger. And you need a precision level of at least 16-bit accuracy
Right.
in your computation. AI PCs don't do this as of today. Right?
Right.
So you can do a 4-bit quantization to get up to 15 billion parameter model,
Right.
but not for these precision applications. And for certain applications, that's good enough. And so the argument today is, if you want it to be highly accurate, go to the cloud. If you don't, then use an AI PC. That's not what you want. That's not what I want. I want whatever I do in my PC to be as accurate as it would be in the cloud. And my simple argument is, if the 4-bit quantization was good enough, why don't we do it in the cloud and save 1/10 the power, right? 10x the power.
Right.
Why would you not do it? And the simple answer is because nobody wants it. Otherwise, you would have done it. So,
well, it's the old argument, like the 4004 when it came out, and then the 8008 when it came out, and then the 80 what's a 16-bit version of 80? Is it 85? Is it? And then going up this this
the
cycle.
curves, yes.
Yeah. So fantastic. So now let's go down. You're an experienced, seasoned serial entrepreneur, and you've obviously looked at the issue of the IP side of it. Describe a little bit about your approach in your first company, when you did it 20 years ago with a lot of patents, and how are you doing it now as a kind of a bootstrap founder?
Mm-hmm. So when we did our first company, right, that's when I approached you to get the help on IP. We actually came up with a fairly novel idea that did not exist. This is 20 some years ago, right? We came up with the first concept of a 3D chip. Now everybody is doing 3D chips. Those days we didn't even have software to do a 3D chip.
Right.
We had to build two chips in two separate databases and figure out a technique how we can actually put one on top of the other,
Right.
because there was no EDA software tools that allowed us to
True.
do something. So we learned how to stitch it, some rudimentary technique. Because of that, we end up with a lot of IP. I
That's
think
right.
if I remember right, as a startup company, we had something like 60 patents, like in
Yep.
2 years of our
Yeah,
work.
that was a lot.
Which was a lot. So, so the IP became important for two reasons, and the primary reason was I was very reluctant to go in front of venture capital and all these other people and throw out a brand new idea that did not exist, because you'll be surprised how quickly
They spread.
word spreads and how quickly things get imitated and copied.
Absolutely.
As an example, when I came up with the 3D FPGA, 2 years later, I actually found research papers in IEEE journals talking about 3D FPGAs. Because some faculty member picked up that idea, put graduate students and started doing research in this area. Fortunately, when those papers came out, I already had 20 odd patents issued.
Right.
So it didn't make any difference, because everything that they said, we had already covered in our
Then they probably
patents.
cited to your patents.
Yeah, so it kind of fell apart. So the same concept happens now, because when we started this idea of saying, how do you do AI in a CPU? Remember, it doesn't exist. Nobody does AI in a CPU.
Right.
It's a brand new concept.
term.
People do AI in a CPU plus GPU, in a CPU plus NPU, in a CPU plus something.
That's right.
Never in a CPU.
Right.
So we had to cover that area, and obviously we don't have so much money to go and spend a lot of these efforts doing that, right? So the approach I take is, as inventors, we generate the ideas, and as attorneys, we find somebody who's good with the language to figure out how cost effectively
Exactly.
make these into patents and file them. And the more difficult part is not so much writing the patent, it's getting the language right. And also when the patent attorney from the patent office says, no, we don't agree with your language here, we don't agree with your language there, how do you rebuttal? How do you go back to them and say, no, you overlook this, you overlook that? So that partnership, I think, is very important, because there's I don't have the clarity of language, how to state what I want. I have a good technical understanding of this is what I want to say, but this lot of patent attorneys, it's never, I think 90% of the time, it's not the technical argument. It's always a language argument, because you're not covering your technical content accurately in the language that you use to describe what you're trying to describe, right? So getting that is tricky. It's very easy to write things very narrowly, but it's a lot harder
To get it broad.
to make it broad
and get it past the patent
and
office.
then you have to be able to figure out what else are you going to cover, right? How else can somebody else sneak into what you're doing? So that involves quite a bit of thinking.
So the way many patent lawyers, what they do is they just do paper back and forth with the patent office, never talk to the examiner. I, on the opposite side of it, love to communicate with the examiner. The first thing I do is, let me call the examiner up and set up a meeting. What is your experience with that process?
So I was actually very surprised when we did that before, right? Because I think before we did it in even the last company, for a few iterations, I've been doing it without that consultation with the examiner, going back and forth. So going with the examiner, the first thing I discovered was it wasn't the concept he was challenging, it was the language he
The
was
wording,
challenging,
yes.
right? So as a result, it allowed us a little bit more time, and having you there to walk through it, to understand the language, to get the clarity into the language so we can file it better, so we can respond better.
Yes.
Was a huge improvement. It avoids all these iterations and going back and forth.
And it saves you
cuts
money
it
and
down.
it speeds you up.
It saves money, time, my effort, even the examiner's time and effort
Exactly.
in going this. And as you walked in, I told you, right, we got our first patent today.
Congratulations.
Thank you very much for helping us get that. So I'm very happy with that particular patent. And that specifically goes into this distinction of how do we make an AI CPU work from a architectural point of view, from the way things are hooked up in the computer, in the CPU, right? It talks about new ways of hooking up computing elements so that they can talk to each other in a different technique.
Right.
From what everybody else has been doing in CPUs and GPUs and FPGAs and all these ASICs and all these other types of computing techniques.
Right. So I imagine you're going to replicate on, the same formula, doing more, doing cost effectively. When you bundle all this and you go to an investor, how do you kind of position the company?
So investors primarily they look for what is your key idea. Second, they look at it, what is the key market segment and how do you enter the market segment. Once they are done with those two, the immediate next thing is, so what is that IP? Can anybody just slam dunk and do this, right? So what is the big novelty of what you're doing? So, and how are you protecting it? Right. So it's very key at that point to get very broad language on some of your basic key ideas so that it prevents large groups of companies enter. Right. Because the idea is very broad. If you end up with a very narrow idea, for example, I'm trying to do an in-memory computing thing. So what is your novelty? I have this element that can give me in-memory computing a better advantage over somebody else. So what if somebody else comes up with a different element? Well, of course they will, because you're not unique in memory computing because it existed before a CPU.
Right.
40, 50 years ago, people are doing in-memory computing, right? So then your advantage is not that great, and then somebody else could duplicate it. And I always say, man, all these rich companies that are worth close to $1 trillion, you think they can't do it by tomorrow if they wanted to, right? The reason they're not doing it is they don't want to, because they don't see a value in it,
right?
Because it's so easy to do, right? So they're not too bothered about doing things like that. So as a result, it's not worth doing.
Yeah, well, and your patent portfolio now would present value to, let's say if there's a company trying to enter the space, they have to compute the risk of infringing your patent or stay out of it or acquire it.
Exactly. You become you're better off acquiring it.
Yeah, it's cheaper to acquire than to design around if you have a big portfolio. So that's probably why you're doing so many, 60, 70 on the first one. So yes.
So Bao, get ready for another 60 or 70.
I'll be glad to.
We've only filed 10 so far, so we have another long way to go, right?
Yeah, you're one issue, so that 9 more to go.
9 more to go.
Yes.
And then 40 more to.
Yep. Well, fantastic. Well, thank you so much for the time and
My
sharing
pleasure.
us your experience.
Yes.
Well, I'm sure you're going to be successful.
Thank you very much for having us. And
all right.
I appreciate your help and advice and getting us moving in the right direction. Yeah.
It's a pleasure.
Thank you, Bao. And not to mention trademarks. Thank you.
Yes.
They're getting harder to get.
Great.
Yeah.
Well, thank you.
Bye.